Hi, I'm Mason Bell, and today I'll be talking about our lab's current and future developments as we assess telerobotic assembly recovery using virtual training for low-latency lunar applications. This work is led by myself, Arun Kumar, and Phaedra Kurlan under the direction of Jack Burns at the University of Colorado Boulder. To provide a brief introduction, NASA has set goals to return to the moon and create a sustainable lunar presence. With this in mind and the implementation of the Lunar Gateway, low-latency telerobotic operations on the lunar surface will become very important in the near future. Current applications on foreign bodies leverage hardware duplicates to address failure response. The Mars Yard, a Martian terrain duplicate on Earth, is used to replicate the current state of the Mars rover to best assess the problem at hand. The developed solution is then communicated to the Mars rover via command sequencing. Our lab has set a goal to develop effective and efficient real-time failure response methods leveraging virtual reality. With this in mind, our main research objective is to simplify the process of planetary robotic failure recovery by developing our virtual recovery simulation. Our robot, Armstrong, consists of a 6 degree of freedom robotic arm and differential drive base. The Z-Mini, a stereoscopic camera, provides local stereo pass-through to the operator viewed through an Oculus Quest. This robot will be replicated within our virtual simulation and also used by the operator for physical failure recovery. To address our research objectives, we are in the development of a virtual recovery sandbox. Using accurate CAD models of the rover, we've been able to recreate a moving model of Armstrong within our virtual space. 3D scans taken from the Z-Mini can also help to recreate a virtual space representative of the robot's current state and environment. Once in the simulation, the operator may view the environment and assess the problem from an exocentric third-person standpoint. The operator may also control the rover from the egocentric standpoint, viewing through the eyes of the rover. In this simulation, the operator is able to move freely between perspectives, as well as reset the simulation to the initial state. This creates a risk-free solution development environment. As we'd like to compare our virtual sandbox to current failure recovery methods, we've also created a physical recovery sandbox similar to the Mars Yard. Using a hardware duplicate of our rover in a reconstructed environment, operators are able to assess the problem with the ability to interact with hardware. Finally, I'd like to directly address the benefits of virtual recreation. As real-time operations become more applicable, the ability to create representative virtual environments will heavily benefit the operator. This is also a cost-effective solution as it's completely virtual. It is also notable that within a virtual simulation, we have the ability to replicate and modify physics and gravity to best fit the environment. Going forward, we intend to put our model to the test. We will be running an experiment to validate the effectiveness of virtual recovery training by comparing our virtual recovery sandbox to traditional failure recovery methods. By validating our model, we hope to support future lunar missions and real-time telerobotic applications in the near future. Thank you.